Thank you very much, Mr. Ramcharan, for your very kind introduction. And good afternoon, all. It's a great pleasure to be here in the Business Science Center in Calicut. When I was a student in Melbourne School, more than 20 years before, a bus from the Business Science Center came to my school. I still remember one interesting experiment which had two linear polarizers which you could rotate. One is fixed and the other is rotated. And if the polarizers are aligned with each other, you could see the light coming from behind. If they are aligned opposite each other, it becomes completely dark. And I was told that the windows of airplanes use this technique. So the first time I bought an airplane was 10 years after that, but I never managed to see one in the airplane until now. This is the only time I've seen a very nice use of polarizers. It's a great thing to come back to this Business Sciences after 25 years of seeing a polarizer. And you will also see that the gravitational waves also are polarized. They also just like light. They can have polarization states. I briefly mentioned when I refer to this. So thank you very much. So since this is also a place of astronomy where young people get a first view of astronomy, I thought it's appropriate to start my talk by essentially remembering what astronomy was 15,000 years before or 17,000 years before. So well before human beings invented telescopes, people started looking at stars and must have wondered about it. So this is a cave painting from a cave in southern France. And I actually see that in one of the exhibits in the planetarium also. So you see that now, ancient human beings wondered about many things around them, like animals, humans, everything, etc. But if you look closely, there are these little dots here and here. And the historians and archaeologists still debate on what these dots could be. One possible explanation is that these could be stars. So people did look at the night sky and wondered about stars and then made an imprint on them. So they record in their paintings. So you can see this in the paintings. But really the modern astronomy began about 400 years before by the invention of the modern telescope by Galileo Galilei. This is the first telescope that Galileo made. And such a simple instrument, once we started looking at the sky with a simple instrument, it just opened up a completely new window to the universe. So Galileo looked at the Jupiter and saw moons of Jupiter orbiting the Jupiter, not the Earth or the Sun. So this basically completely changed the worldview of the times and eventually led to what is called the scientific revolution. So which all the modern technology and modern science basically came from this time, the so-called scientific revolution. And in the 20th century, people, of course, the Galileo people started making telescopes with bigger and bigger sizes. In the 20th century, the astronomical observations using electromagnetic waves, not only the visible part of the electromagnetic spectrum, but other wavelengths of the electromagnetic spectrum, such as infrared, radio waves, X-rays, gamma ray, etc., became possible. And each of these observational windows provided us a completely different picture of the universe. So let me just give you a few examples of the universe looked at different frequencies of the electromagnetic spectrum. So this is our familiar optical light, the visible light. So this is something that you will see typically in a planetarium, for example. This is a galaxy basically. They all use a particular coordinate system in which the galaxy, which is basically a disk, most of the stars in the galaxy are basically distributed in disk. This disk is basically given as this horizontal middle. And if you look at, for example, the sky in a different wavelength, for example, in the microwave region, you can basically see the universe at its very young age. This is called the cosmic microwave background radiation. This basically came from a few 10,000 years, a lakh, 100,000 years after the Big Bang. This is how the universe did look like. These colors are the small temperature fluctuations, small pieces of excess temperature and reduced temperature in the sky, which actually basically created what we call the perturbations, which became stars, galaxies, and so on. So I didn't want to explain all of these thoughts, but I wanted to say that basically if you look at the universe in a particular, in a different wavelength of the electromagnetic spectrum, you basically look back at different times, you get access to very different phenomena, which sometimes you will see this phenomena only by looking at using a telescope that works in that part of the electromagnetic spectrum. Now recently, so I think it's fair to say that most of the things that we know about the universe and many of the modern physics essentially came from observations of electromagnetic telescopes, from optical, radio, X-ray, gamma rays, etc. But recently, astronomical observations using non-electromagnetic messengers also have become possible. This is something very recent, the last 15 years or so. So this is, for example, a sky map, basically again, mark these points in the sky of the arrival directions of what is called the ultra-high energy cosmic rays. These are extremely high energetic protons or heavier nuclei, for example, which are coming from somewhere out of space, which we don't have an idea about, and producing certain detections in large detectors. This is from a particular observatory in Argentina called the Alger. And these black dots are the arrival directions of these ultra-high energy cosmic rays. And nobody really knows where these are coming from. So people try to do a lot of things to understand what is producing these energetic events. And there, for example, these blue are other electromagnetic observations of what is called the active galactic nuclei, which are the centers of galaxies. We are trying to see, for example, if it turns out that all these black dots are on top of blue dots, then this is a very strong indication that these ultra-high energy cosmic rays are coming from galactic centers of galaxies. There is a black hole at the center of galaxies. But they are not, right? So these black dots and the blue dots do not really coincide. So it's still not clear what is producing these things. So I just want to another example is the observations of what is called the high energy neutrinos. Neutrinos are another subatomic particles, they're very hard to detect. And this is detected by a very fantastic observatory called IceCube, which is in the Antarctica. So basically what they have to do is they have drilled holes of kilometer size in the ice of Antarctica and place several detectors. And when these neutrinos pass through the ice, they're extremely transparent, like a glass. It produces a particular light called Cherenkov radiation, and these detectors detect that, and by this enables scientists to detect these neutrinos as well as to locate the direction of these neutrinos coming from the sky. Again, there are a number of possible candidates for producing this high energy neutrinos, but still people don't know what is producing this high energy neutrinos. So these are really the baby steps of certain branches of astronomy which are happening over the last 5 to 10 years. And really, the last one I wanted to show is the first sky map, the first look of the sky using gravitational waves, which I will talk about later. This is basically the reconstructed location of the first gravitational signal produced by the mergers of two high-mass black holes, which the LIGO observatories in the US detected in September last year. It was announced only last week after 5 months of careful analysis by the LIGO scientific collaboration. Okay, now let's try to ask what are gravitational waves. So before I tell you what are gravitational waves, I have to tell you what is Einstein's theory of gravity. So the general theory of relativity proposed by Albert Einstein about 100 years before is the most accurate theory of gravity available to us now. It basically improved upon Newton's theory which was proposed 300 years ago. So what Einstein tells us, according to this theory of Einstein, gravity is a curvature of space-time. So whenever there is a massive object for example, the apple sits in somewhere, it basically bends the space-time around it. So if you imagine this space-time, actually the space has 3 dimensions, the time has another dimension. So it's very hard to visualize that. But let's imagine that the space has only 1 dimension. The time has this other dimension. But if you imagine the space-time is something like a rubber field, and if you place something on that, like a massive object, it will bend the rubber. Right? For example. Now, you can actually measure. It's a very hard concept to grasp that something is curved space-time. But it's something that you can actually measure. So, for example, what is the property of a flat space? So, we all study in school Euclidean geometry. There are several axioms of Euclidean geometry. One is that if you draw a triangle, and if you basically add some of the angles of, or the 3 angles of the triangle, it adds up to 180 degrees. Now, if you do it on a curved sphere, curved surface, for example, on the surface of a football, and if you add up if you draw a triangle on the surface of a football, and if you add up the numbers, the angles, it turns out that it's more than 180 degrees. So the axioms of Euclid is valid only for flat spaces. So what happens is that due to the gravity, the space-time curves. This means that the axioms of the Euclidean geometry is no longer true. So if you, for example, draw a triangle very close to this massive object, for example, this apple, it turns out that you can actually say that, you can actually see that the axioms of Euclidean geometry will not hold up. But very far distances from this massive object, the space-time is approximately flat. So if you draw a triangle here, then if you add up the angles, it turns out that the angles become, it adds up to 180 degrees. So now, this is basically Einstein's remarkable prediction, remarkable theory. It's really a complete leap of faith. That gravity is not a force, but it basically is a theory of space-time itself. Now, so imagine something is moving. For example, a binary of 2 stars orbiting each other, like this. Now, what will happen is that basically the mass concentration is moving around. This is actually, the curvature of space-time also changes, right? Because the mass is moving. Like, for example, if you were to move this apple on your space-time, this disk will move with the space with the apple. Right? Basically, if you have motion of an object, then it will basically create some sort of a motion in the space-time geometry itself. It turns out that these, so for example, if you look at this, for example, this binary star system at the distance, this motion will take some time to propagate. It won't, for example, this change in the motion, the gravity, will not be felt immediately by a distant observer, because according to Einstein's special theory of relativity, nothing can travel faster than light, as we have done. So, for example, if the space-time geometry changes, basically it has to travel the speed of light to distant observer, and these are called gravitational waves. So, basically, gravitational waves are freely propagating oscillations in the fabric of space-time, or freely propagating oscillations in the gravitational field. Just like, for example, electromagnetic waves is a freely propagating oscillation in the electric and magnetic field. Gravitational waves are freely propagating oscillations in the gravitational field. Is this something that's reasonably clear to people? Okay. So, even before the direct observation of gravitational waves by LIGO a few months before, people knew that gravitational waves exist in nature. It's not only a theoretical prediction. There's a very strong body of indirect evidence that gravitational waves exist in the nature. So this came from the observations of what is called the binary pulsar. A pulsar is a neutron star. It's an extremely compact star that can have a mass comparable to the mass of the sun, and the radius a few tens of kilometers, 20 kilometers. So imagine something as big as our sun, which is a million times more massive than the Earth, is compressed into a sphere of 20 kilometer radius. That's comparable to smaller than the Calicut, the Kozhikode district, for example. So these are called neutron stars, and some of these can produce electromagnetic radiation, radio waves, which are pointed towards certain directions. Like this, for example, is laser pointer. This is pointed, very narrowly pointing towards certain directions, right? And these neutrons are rotating. This means that if we happen to be on the line of sight of this neutron star, this beam of light, I won't show the digital example with this laser pointer, but if we happen to be, imagine a torchlight, it's rotating. When we happen to be on the line of sight of the light, what you see is certain blips, right? Pulses of radiation. Whenever the torchlight is facing towards you, you will see a blip, and then it will go away, right? So you see pulses of radiation. These are called, so basically a rotating neutron star that produces pulses of radiation is called a pulsar. And you can observe this radio signals from these rotating neutron stars called pulsars, and people have been observing these pulsars over the last few decades. The binary pulsar system is a more interesting object. It's a two pulsars orbiting each other, right? So you can see it because of for example, you are seeing this pulse, like there's a one pulse, another pulse, and so on. So basically you can, by observing the pulses, you can basically infer the characteristics of the orbit. You can measure the period of the orbit very, very accurately using radio observations. Now these are actually strong sources of gravitational waves, so they emit gravitational waves. And as a result, they lose energy. So basically they lose their orbital energy into gravitational waves, and as a result, the orbital separation decreases. And when the orbital separation decreases, the orbital period also decreases. Like for example, the planets in the solar system itself. So we know that the Mercury is orbiting much faster than the Earth, right? So it's a simple Kepler's law. It's basically the same way. If the orbital separation is decreasing, this means that the orbital period also will decrease. They will rotate faster and faster. And people have observed these binary systems over the last 32 years, something like that, over radio. And they have seen that the change in the orbital period of the system is exactly in agreement with the prediction of Einstein's theory, because the system is losing energy due to gravitational waves, and it's basically coming closer and closer to each other. So over the last 36 years, the location of the has reduced by a few tens of seconds, like 10 seconds. With an accuracy of like 0.1%. This is a very remarkable success of the theory as well as the astronomy. Having a measurement of this accuracy is a very remarkable thing in astronomy. So people who basically did this work or discovered this binary pulsar system got a Nobel Prize in 1993 to discover this binary pulsar system. No, what has been happening over the last 20 years is, while this is basically an indirect evidence of the existence of gravitational waves, because we have not seen a gravitational wave in the system. We have only seen the radio observation, we have seen the radio waves in the system, which gives us indirect evidence that gravitational waves should exist. And what has been happening for the last 20 years is basically a worldwide, an international effort to detect gravitational waves directly on Earth. So this basically works on a basic principle that when a gravitational wave passes through, for example, if a gravitational wave is passing perpendicular to this pole, it stretches the space in a very characteristic way. For example, if you arrange something like a ring of particles, text particles, and in initially a circular shape, it basically deforms the space in such a way that the circle gets elongated in one direction and compressed in the other direction. circle gets deformed into ellipses like this, like shown on this animation. Now, and such a deformation, so this is a characteristic of the tidal force. For example, we know that the tides in the ocean are created by the tidal force of the moon, right? So originally this water around the earth is basically around in a circular way, like a spherical way. But due to the tidal force, this water gets sort of deformed into an ellipse. So it's when you get high tides in the region and low tides in some other region, etc. So it's a very similar effect. The gravitational wave is basically gravitational waves are simply propagation of tidal forces. So this can be detected by using something called a Michelson interferometer. So an interferometer is a system. An interferometer basically involves a laser beam. That is, a laser is here, which is shining on a beam splitter, splits the laser light into two orthogonal directions, here and here. And this gets reflected by two mirrors that are placed at the two ends, and then they will be reflected backwards. So one second. So a laser beam is shining on this beam splitter, split into two orthogonal ones. They get reflected back by the two mirrors, they combine here. And this will produce what is called an interference, right? So initially you can adjust the length of these two arms in such a way that these two interferences happen destructively. They basically kill each other. So as a result, you basically, if you observe here, no light comes up to the interference. It's for a dark hole. Right now, this is something that you do in a college experiment also. So when a gravitational wave passes, one arm gets stretched and other arm gets compressed. Remember that the circular shape here can deform into one arm gets stretched and the other arm gets compressed. This will introduce a relative change in the path length of the light between the two arms, which will change the interference pattern, which you can read out by reading the light that is coming out of the interference. So this is how these interferometers try to detect gravitational waves. This is a very well-established sort of technology because this is invented by Michelson more than 100 years ago, and we still use it. Right? So you can experiment, you can do a tabletop in a college lab, for example. But the challenge is that the expected distortion of the string or the interferometer or the space-time are extremely tiny. Right? So what I was saying that, if you originally lock this interferometer in the steady state where both arms are equal length, and when a gravitational wave passes, it gets deformed into one arm gets stretched and the other arm gets compressed. So imagine that this original length is from L, so let's say 1 meter, and due to the gravitational wave, it makes a small change in the length, which is delta L. Now, the expected strength from realistic sources of gravitational waves from astrophysics is extremely small, just delta L by L of the order of 10 to the minus 21. So 0.21 zeros and 1. So this is the kind of that changes the length that we are trying to measure using this instrument. So no wonder that this is really the hardest measurement problem on Earth. And these interferometers are the most sensitive measurement devices ever constructed. Just to give you a scale of probably this 10 to the minus 21 or if you have a tabletop interferometer, this is essentially this means that you have measured lengths of the order of 10 to the minus 21 meters. Okay. Even if you have a interferometer with a 1 kilometer arm, L-shaped detector 1 kilometer, 1 kilometer, a gravitational wave will introduce a small change in the length, just of the order of 10 to the minus 18 meters, just 0.180 and 1. So this is an extremely small number. If you want to get a sense of this, the atom is of the order of 10 to the minus 10 meters. It's about smaller than a nanometer. We always hear about nanotechnology. Nanotechnology deals with things of nanometer size. Now, a nucleus of this atom is a factor of 1 lakh smaller than this. 1 lakh is about 10 to the minus 15 meters. Now, the 10 to the minus 18 meter, that this length change that is to the path to the gravitational wave, it's a factor of thousands smaller than an atomic nucleus or a proton. So this is really the type of sensitivity that we are talking about in detecting gravitational waves. So it's no wonder that Einstein thought that it's impossible to detect gravitational waves. He didn't put any CPS thought on the gravitational waves. He was convinced that this could ever be detected. So Einstein did not really talk about gravitational waves after his paper. Now people have built these remarkable instruments at several parts of the globe. And in particular, these are so-called LIGO detectors, which made the first I will not miss my. I think I'm loud enough. So these detectors are L-shaped microscope difframeters with 4 kilometer arms. So each arm is 4 kilometer long. And these detectors have been working over the last several years. But what happened recently is that there's a major upgrade in the sensitivity of these instruments. It's called the advanced LIGO, which meant that we were able to see much farther in the universe. Gravitational wave, collisions of black holes happening at really long, really distant parts of the universe. That made it possible to make this first detection of gravitational waves. Okay, on September 14th of 2015, and around 3 p.m. Indian time, the 2 LIGO observatories, which are shown here, two different, almost the ends of the United States, America, detected a coincident gravitational signal. So these signals arrived at these two instruments with a time delay of 7 milliseconds. And this was a really loud signal, so because we always have noise in instruments. For example, if you tune a radio station, sometimes you get noise, right? So you basically need your signal to be louder, much louder than noise, to clearly hear what the person is talking about, or a song, etc. So this is a signal to noise ratio. If you want to make a confident detection, you have to have a good enough signal to noise ratio. And the combined signal to noise ratio, this signal was of the order of 24. It's quite loud in many sense. So, okay, you will because these gravitational waves have a frequency that is in the audio frequency band, about 10 hertz to a few hundred hertz. It's actually possible to convert the observed signal to a sound and possible to listen to it. So you will hear the plot of the signal as well as the sound of it. So it's very hard to listen. It's very hard to hear for the first time. So you will first use your bare thumbs. Though to make it more clear, the frequency has been changed a bit. Then you will hear it better. Then you have to play the original sound back. So that's what this thing is. First what we hear is the noise instrument, the sound. Then you see a thing, and that's what the gravitational wave does. So initially you will hear only a bass, like a thump, but then the frequency is changed so that you can hear it slightly better. I will try again. The whole thing starts only lasts for only a fraction of seconds. So, although the whole thing lasts only for a fraction of a second, like 0.2 seconds, it's possible to, this contains remarkable amounts of information. So this can tell a lot about the sources of the source that produces this signal. So for example, this is how the signal looked like in the difframeter. You make a plot. This is the time, for example, like the time. About the whole duration is about 0.2 seconds. And this is the amplitude of this observed signal, the two detectors. You see here, the Hanford detector and the Livingston split, two LIGO detectors. And this is what the Einstein's prediction was. So this one and this one. So these two are the expected shape of the signal as computed by the theory of Einstein that comes from these two black holes. So you can see that they agree remarkably. Even by looking at the observed data by the theoretical prediction, you can see that the consistency is very good. But of course, our analysis is not based on looking at the data, and actual analysis is much more sophisticated and much more rigorous. And nobody really expects that you could see a signal in the data, because we require a lot of computer processing to pull out the signal in the data. Only because this was such a loud signal, that it was possible to make a plot and see the signal in the data. This is already a very remarkable observation. And just by looking at the data, you can see that there is a gravitation wave, and this has to be from a binary black hole. So what we have seen by looking at the observed the data, the scientists are able to extract a large amount of information from the signal, and they concluded that this signal came from the collision of two black holes happening in a distant universe. It's about 1.3 billion light years ago. So this event happened 1.3 billion billion years, and at a distance of 1.3 billion light years, because the gravitation wave travels at the speed of light. So this has been traveling over the last 1.3 billion years, when there was no dinosaurs even in the Earth. Only the multicellular organisms were starting to grow on Earth. So this happened at such a distance past, and it was been traveling all these years, and it arrived at the detector last year on September 14th. So basically the phenomenon is the following: there are two black holes that are orbiting each other, and in this process they radiate gravitation waves, and just like this pulsars, they lose energy and they become closer and closer, and eventually these two black holes collide with each other. They merge to produce a single black hole. And this is the expected signal calculated from expected gravitational signal from such a phenomena computed by the theory of relativity. And the observation agrees remarkably well with the prediction of Einstein's theory. So, the signal arrived on the 14th of September, and after 3 minutes of the arrival, essentially all members of the collaboration knew that there was a possible gravitational signal. But it took 5 months for us to announce the discovery, because all this 5 months was spent on making sure that this is really a gravitational signal and nothing else would produce a signal like this. Because a large number of environmental disturbances could potentially produce a signal, a fake signal in the detector. So you have to really make sure that really nothing else could produce a signal, and this is indeed a gravitational signal. And in science, you could never make, nothing is settled. Your truth is always tentative. Because you can, if you say something 100% right, this is not science. Because science is always improving and getting closer to the truth. So we cannot say that this is a gravitational signal with 100% certainty, but we can say that with a very, very high amount of confidence that this is a gravitational signal. So the confidence, the probability that something other than an astrophysical source producing a signal is 1 part in 1 crore. ഒരു കോടിയിൽ ഒരു ഭാഗം മാത്രമാണ് നമ്മുടെ possible false alarm probability. So it's an extremely small number. So we are very, very confident that this is actually a gravitational signal. This is based on 5 months of rigorous analysis by a 1,000-member collaboration. So this is actually this is so much related to the popular culture that the New Yorker magazine is one of the oldest magazines in the world, has produced a cartoon based on this discovery. And I'm very glad to say that Amul, if you follow the Amul advertisement, the Amul, some very ingenious person draws cartoons for Amul, and many of these things are based on current affairs. If there's an interesting news on the front page, you will see an interesting cartoon on the first page newspaper, which is an advertisement for Amul. So this is the discovery of gravitation wave even became a cartoon for Amul. Like when I was driving yesterday, I saw a big billboard with Amul's advertisement, which carried a cartoon on the gravitation discovery. Something that is very rarely happens, that a discovery in science makes it to the popular culture in the next 3 days. So, so this characteristic signal, I can explain this cartoon slightly better. This particular shape of the signal has a very characteristic shape. You can see that the amplitude of the signal is increasing. So is the frequency. The wavelength is decreasing. Right? Wavelength will largely so it's like the frequency of the signal is increasing as well as the amplitude. And this is the same characteristic of the chirping of birds. Pakshigal's shabdam, they time frequency characteristic. So this is called chirps. No, this is called a gravitational chirp, for example. It's very commonly used in the field as a gravitational chirp. So the cartoon says that two birds are speaking to each other, and one is saying that, was that you I heard just now, or was it two black holes colliding? So, but it's actually true that a number of environmental disturbances produce a fake signal in our detector, like seismic motion, for example. The Earth is vibrating all the time. Magnetic fields, acoustic noises. So if there's a train that is going on in a neighbor train field, in a train track, it can produce a signal there. So we really have to be, so the way that this instrument works is that there are something like 10,000 environmental monitors in the form of seismometers, microphones, magnetometers, electric field sensors, etc. It all records the data, about 10,000 of them. So we have to make sure that this signal is not found in any of these other ones, to really make sure that this is indeed a gravitational signal. Such an exercise has been performed very rigorously, and it ruled out the possibility of anything other than the gravitational signal. So, and I said that this data contains, this basically 0.2 seconds of data, just like type, contains remarkable amount of information. So by looking at this, by comparing the shape of the observed signal with theoretical predictions, we have inferred that the signal essentially came from the collision of two black holes that has mass 36 times the mass of the sun. So this particular symbol, M O dot, stands for the mass of the sun. It's about 10 to the power 34 kilograms, something like that. So these two black holes had masses of 36 and 29 times the mass of the sun. They merged to form a single black hole that is rapidly spinning, rapidly rotating. And the single black hole had a mass of 62 times the mass of the sun. And that is rapidly spinning with the rate of 67% the maximum possible spin of the black hole, very rapidly spinning black hole. So this is for the first time we are seeing a direct evidence of black hole. There have been a number of indirect evidence of black holes. It's the first time we are seeing the mergers of two black holes, a binary system where two black holes are orbiting and merging from a single black hole. And this is the first time we are seeing black holes with this high mass. So in the stellar mass database, there are two sort of classes of black holes that we know exist. So one is has mass a few times the mass of the sun, 10 to 20 solar masses. And another type of black holes have masses millions of the mass of the sun. For example, these black holes are the centers of galaxies. But there was no previous evidence that black holes with masses 30 to 60 solar mass existed before. This is the first time that we are seeing black holes of this mass. So I'll skip this more technical details. So another remarkable thing is that something like 3 times the mass of the sun is converted into energy in this merger process. We know that I think the most popular formula for physics is E equal to mc squared. Right? So something like the M, imagine a M of 3 solar mass converted to energy. So the whole sun is basically, suppose the whole sun is burned to produce, completely transformed to energy in a fraction of seconds. So you have basically 3 suns converted into energy in a fraction of seconds in this merger process. So this is the most sort of luminous, the most powerful astrophysical phenomena happening in the universe. So if of course, this does not produce any light. But the power I'm talking about is the power in gravitational waves. All this energy is converted into gravitational waves. So if you want to make a comparison, if you take all the stars of the universe, Right? There are 10 to the power 10, 11 stars in every galaxy roughly, and there are 10 to the 11 galaxies, 11 zeros. So I'm talking about 1 after 22 zeros of stars. So if you put the luminosity, the light from all the stars put together, the power radiated in this event is larger than the power radiated by all the stars in the universe. This is by far the most luminous astrophysical event that we have observed. Okay, and this signal for the first time allowed us to test Einstein's theory in a very different regime. So, as we heard earlier, the scientists, one of the biggest dreams of scientists is to prove Einstein's law, right? But this was not possible until now. So, but because Einstein's theory is one of the pillars of modern physics. But as while we all work with a theory, in science we never take a theory as a proxy of absolute truth. It's very different from a religion, where you have a holy text, you take it and it's absolute truth. It's very different in science. None of the theories are fundamental enough, fully right. So they are always some sort of approximations of truth. So it's always, while we use theories, scientists always test these theories using more experiments and observations. It's a very integral part of this error correcting mechanism that science has built into. So for the first, Einstein's theory has been tested by a number of experiments and astronomical observations in the last 100 years. And the theory has been passed all these tests with flying colors, all first class. But all these tests were performed in regions where the gravity is mostly weak and the objects are moving at rather small velocities. And this is for the first time, this has provided us to test the theory of Einstein in a regime where the gravity is extreme, the velocities are also extreme. So for example, during the last stages of this motion of these black holes, they were traveling at about half the speed of light. We are very extremely relativistic events. One thing that is constant in the universe is the speed of light. Right? So if that is unaffected by anything. So if a length is changing, the speed of light is constant. It takes a longer time to come. It doesn't affect the gravity. But light can bend due to the gravity. But basically, that's a very small effect.
So how do you understand there is a black hole, two black holes at long distance, infinity? Could you detect that two black holes?
Yeah.
Sir, after ദൂരത്ത് രണ്ട് black holes ഉണ്ട് എന്ന് മനസ്സിലാക്കിയത് എങ്ങനെയാണ്?
അതെന്താണ് കാര്യം? ഞാൻ പറഞ്ഞത് നമുക്ക് ഈ black holes in the gravitational fields we can calculate using Einstein's theory. അപ്പോൾ ഈ gravity black holes ന്റെ mass for example change ചെയ്തു. So if രണ്ട് black 30 and 35 and 29, suppose you collide two black holes, masses 1 and 3 solar. Their signal shape will be very different from what we have seen here. ഈ ഓരോ gravitational waves, ഓരോ source ന്റെ signals different. So what you do is you compare the data with millions of copies of gravitational waves corresponding to different masses of black holes, different properties. And you take the best one, the one that takes the signal template that matches best with the data. That's how you infer the masses of the black holes. Okay. അതായത് ഈ ബ്ലാക്ക് ഹോളിനെ നമ്മൾ ഇൻഫർ ചെയ്തിരിക്കുന്നത് ഈ ബ്ലാക്ക് ഹോളിൽ ഈ സിഗ്നൽ പ്രൊഡ്യൂസ് ചെയ്തിരിക്കുന്നത് അതായത് collision of two black holes. One has a mass of about 30 times the mass of the sun. Other also has a mass of 35 times the mass of the sun. Now imagine a different type of two black holes. One with mass one solar mass, two solar mass, you can compute this gravitational signal from this. And that will look very different from what we have seen in the table. ഇതാണ് നമുക്ക് തിയറി ഉണ്ട്. ആ തിയറി വെച്ചിട്ട് എക്സ്പെരിമെന്റിൽ കാൽക്കുലേറ്റ് ചെയ്യാൻ പറ്റും. ആ തിയറിയുടെ പ്രഡിക്ഷനിലുള്ള ഒരേ സാധനമാണോ ഡേറ്റയിൽ കാണുന്നത്. ഇത് വെരി ഡിഫറെന്റ് ഇൻപുട്സ് ആണ്. ഇതിന്റെ എഗ്രിമെന്റ് ആണ് ഇതാണ് ബ്ലാക്ക് ഹോൾ, ഇതാണ് ഈ സിഗ്നൽ ബ്ലാക്ക് ഹോൾ പ്രൊഡ്യൂസ് ആണെന്ന് പറയുന്നത്. ദൂരെ കൂടുതൽ ഗ്രാവിറ്റേഷൻ സിഗ്നലിന്റെ ആംപ്ലിറ്റ്യൂഡ് കുറഞ്ഞുകൊണ്ട് ഹാർഡ്
ഒരിക്കലും മാത്രമല്ല ഡിറ്റക്ട് ചെയ്തത്. അപ്പോൾ എററാണ് നമ്മൾ ഡാറ്റ കളക്ട് പല ഡിറ്റക്ടേഴ്സ് ഉണ്ടാവും. ഒരിക്കലും ഡിറ്റക്ട് ചെയ്ത് വെച്ചിട്ട് ആക്യുറേറ്റ് ആയിട്ട്
So there are the signal has been observed in two detectors which are separated by 4,000 kilometers. LIGO detectors are at very different locations. These are separated by 4,000 kilometers. The same signal has been observed by two detectors. And also, the same signal agrees exactly with the theoretical prediction of the field. It's very hard for anything else to make that theoretical prediction as well as to produce the same signal in the two detectors that are separated by 4,000 kilometers.
Center of the universe is the concept.
There is no such thing as a center of the universe. Essentially working knowledge is that the universe is homogeneous and isotropic, basically at large scale. And at large scale of the universe looks like the same everywhere.
See, രണ്ട് മാസമായി പ്രവർത്തിക്കുന്ന റിലേറ്റീവ് ആയിട്ടുള്ള മോഷൻസ് മാത്രമാണ് ഈ ഗ്രാവിറ്റേഷൻ വേവ്സ് ഉണ്ടാകുന്നത്. അല്ലാതുള്ള റൊട്ടേഷൻ ബ്ലാക്ക് ഹോൾ ഇപ്പോൾ ഇതിന്റെ സെന്റേഴ്സിൽ മാത്രമല്ല അല്ലാത്ത സ്പേസിലും ഈ ബ്ലാക്ക് ഹോൾസ് ഉണ്ട്. അപ്പോൾ എന്ത് കാരണമാണ് ഈ ഗ്രാവിറ്റേഷൻ വേവ്സ്?
So if you ഒരു ബ്ലാക്ക് ഹോളിനെ സ്വന്തമായിട്ട് റൊട്ടേറ്റ് ചെയ്ത് കഴിഞ്ഞാൽ it doesn't produce any gravitation waves because you need to have something called a time varying quadrupole.
ഗാലക്സി സെന്ററിന് ഇതായിട്ട് റൊട്ടേറ്റ് ചെയ്യുന്നത് എന്ന് വെച്ചാൽ റിവോൾവ് ചെയ്യുന്നത്. അപ്പോൾ അതുകൊണ്ട് ഗ്രാവിറ്റേഷൻ വേവ്സ് ഉണ്ട്.
Actually, in the motion of masses can produce gravitation waves. If I move my hand, this is producing gravitation waves. It's extremely weak, so you cannot detect them using any conceivable technology. So if you want to produce a loud gravitation wave, you need to have a very massive system which is extremely compact, extremely dense, that is moving at very high speeds. So black holes basically fits with all of these. They are very massive, they are extremely compact, and this here they are moving at very fast velocity, close to the speed of light. That's why this is producing the very loud signal.
ഇതിൽ രണ്ട് ബ്ലാക്ക് ഹോൾ വേണമെന്നുണ്ടോ? ഒരു ബൈനറി സ്റ്റാർ സിസ്റ്റത്തിൽ അത് പറ്റില്ലേ? രണ്ട് ബ്ലാക്ക് ഹോൾ ആണെന്നല്ലോ, ഒന്നൊരു സ്റ്റാർ ആണെങ്കിലും ഇത് പോസിബിൾ അല്ലേ?
If you have two stars or one black hole and a star, the star is very massive, but it's very big. It's not very compact. So then the amplitude of gravitation waves will not be very high.
What will be the impact of this detection of gravitational waves in the field of astronomy?
So it's basically this has just opened up a new branch of astronomy. So we have had the openings of several branches of astronomy in the last century. I've shown some examples. This is the newest branch of astronomy, and it's very complementary. The information that we gain from this observation is completely different from the information that we gain from any other fields of astronomy. And some of the information cannot be gained by any field of astronomy. For example, you could never have observed a signal from a true black hole system using any form of electromagnetic because they don't produce any light. So this is the only way of seeing, for example, black holes. And secondly, for example, I showed a picture of the early universe from the cosmic microwave background radiation. And this is a picture of the universe after 1 lakh years after the Big Bang. The reason is that in the early years of the Big Bang, the universe was so dense that it was impossible for even light to escape from it. So basically, the earliest that you can see using electromagnetic waves is 10 to 5 years after the Big Bang. But the gravitation waves could leak out all the time. So if you are able to detect gravitation waves from the Big Bang, you will see a fixture of the universe in the first fraction of a second. So this is in some sense the ultimate aim of the gravitational, and it will take several years.
So that signal will be still somewhere there. That gravitation will be somewhere there.
So but it will have different frequencies, different characteristics. You will have more sensitive detectors to measure this.
How far the detection supports the amplification? How far is it?
So the point is there is no grand unification theory yet. People are working for it. And there are some ideas about the energy scales of the grand unification theory, etc. And if you detect gravitational waves from this early universe, that gives you some very important clues of what is the energy scales of gut scale, etc. But that takes So there are two main groups in India who have been working on the science of gravitation for the last 25 years. One is a group of Sanjeev and Rajat. One is a group of Bala here and Raman Research Institute. They have been really pioneering contributors in developing various techniques in terms of the data analysis techniques, particularly theoretical calculus, that simply form the foundation of this field. So what that's really the last 25 years, at least two groups in India have been making major work. The last 5 years, several new groups have formed a consortium called the Indian Initiative to Gravitational Observation, INTIGO. They are members of the Live Scientific Collaboration. So these groups have made some very direct contributions. For example, I mentioned that this merger has produced a black hole of 62 solar mass and a black hole is a black hole with 0.67 times the speed of the maximum possible black hole in the. So this inference basically came directly from